Welcome to another deep dive. We got a really cool request from a listener wanting us to break down these ideas of centroids and how they relate to the center of gravity and mass and even distributed loads.
Sounds pretty complex, right?
Yeah, it could be, but the listener sent over some really great materials, chapters from what seems to be an engineering textbook.
Okay.
And I think we can definitely make this clear, engaging, and I think immediately useful.
All right, let's give it a shot.
Yeah. So we're going to approach this in three parts. First, we're going to look at how to find the sweet spot of irregular shapes, those made up of simpler ones. These are centroids of composite areas.
Okay, yeah. I mean, we all have an intuitive sense of where the center of something is. Like, think about putting a book on a table. You know, where to put your hand so it doesn't tip over.
Yeah, exactly.
Today, we're putting the math behind that. So you'll have the tools to actually calculate that point, precisely whether it's a simple shape or something way more complex.
Love it. And to kind of set the stage for this, let's start with something we all understand, GPAs.
Okay, how's that going to help us find the center of a shape?
Well, think about it. Your GPA is a weighted average, right? The grades you get in different courses, they're weighted by how many credits each course is worth.
Ah, I see where you're going with this. So in the formula for weighted average, which is AA, the A would be our grades, and the W would be the course credits.
Exactly. And that overall GPA, it gives you a sense of your average performance, but acknowledging that some courses have more influence than others.
Right, because they're weighted more heavily. And that idea of weighting, it's going to be crucial as we talk about all these centers, centroid, center of gravity, center of mass. They're all based on this idea of a weighted average.
Absolutely. And speaking of which, the materials you sent over have this really great example, 7.1.1, where you're trying to figure out what score you need on your final exam to get a specific grade in the class. You've got two exams worth 25% each, homework worth 10%, and then the final exam, the big one, worth 40%. That final exam, it has so much more influence on your final grade compared to, let's say, a single homework assignment.
Yeah, it makes you sweat a little bit more.
Yeah.
But the key takeaway here is that some elements in a system can carry more weight, literally or figuratively, than others, and that's because of their weighting factor. It's not just a simple average. We're taking into account how much each part contributes to the overall picture.
Okay, so let's dive into the center of gravity. We always talk about, an object's weight acting at a single point. Like there's this imaginary spot where all the weight seems to be concentrated.
Right, it's a point where gravity is basically pulling on the whole object. If you could magically put your finger under that point, the object would balance perfectly. That's also what we mean by statically equivalent systems. A single force at the center of gravity has the same overall effect as the weight distributed throughout the entire object.
It's like in that pencil balancing example, figure 7.2.2.
Yeah.
You're trying to find that point where the weightiness on either side of your finger is perfectly balanced so the pencil doesn't tip over.
Precisely. When everything's balanced, that means the moments are balanced as well. A moment is, well, think of it like the tendency of a force to make something rotate. So if the moments on both sides of your finger are equal, the pencil stays put.
So how do we actually calculate this center of gravity?
Well, when you have something made up of multiple parts, like let's say a bunch of boxes stuck together, you can find the x-coordinate of the center of gravity, denoted by x, using this formula, xxiv. Here, v represents the weight of each individual part, and xi is the x-coordinate of that part's own center of gravity. And the top part, xi, that's what we call the first moment of force about the a-axis. Basically, it considers both the weight of each piece and its distance from the axis, giving you a measure of its contribution to the overall rotational tendency.
So the center of gravity is where all those individual rotational tendencies from all the different parts perfectly cancel each other out.
Exactly. And we have similar formulas for tie and zal if we're working in 3D.
Okay, I'm looking at question 7.2.3 here, and it asks why a symmetrical object's center of gravity always lies on its axis of symmetry. It seems obvious, but what's the reasoning behind that?
It's all about balance. A shape that's visually balanced must have its geometric center along that line of balance. In more mathematical terms, if an object is symmetrical, for every little bit of weight on one side of the axis, there's an equal weight at the same distance on the other side. So when you add up those moments, they create equal and opposite rotational forces that cancel each other out, meaning there's no net tendency to rotate around that axis, so the center of gravity has to be right on it.
That's a really clear explanation. And example 7.2.4 with the three boxes along the x-axis really drives this point home. Even if you shift your reference point, like where you place your origin, the physical center of gravity of those boxes doesn't actually change.
Right. Only the coordinates change relative to your chosen origin.
It's a property of the system itself.
Exactly. The center of gravity is inherent to the object. It's not something we just make up based on our coordinate system.
Okay, so now how does the center of mass come into all of this? Is it the same as the center of gravity?
It's closely related. The center of mass represents the average location of an object's mass. It's like finding the balancing point if we only considered mass and ignored gravity. Now, remember Newton's second law?
Yeah, force equals mass times acceleration.
Right. And when we talk about weight, it's a force due to gravity acting on an object's mass. So weight, W equals mass, M times the acceleration due to gravity, G, or W equals mg.
So if gravity is the same across the whole object, that simplifies things, right?
Exactly. If G is constant, when you substitute we mig into the formulas for center of gravity, the G cancels out, and we end up with the formulas for the center of mass, Q sub B, and the same for I and A.
So basically, in everyday scenarios here on Earth, where gravity is pretty much constant, the center of mass and the center of gravity are the same point.
Exactly. They coincide. That's why we often use the terms interchangeably.
Okay, that makes sense. Now, let's shift gears to something called centroids. So this is where we move away from physical properties like weight and mass and just focus on pure geometry, the shape itself.
Exactly. The centroid is like the geometric balancing point. Think of it as the center of a shape, whether it's a line, a 2D area, or a 3D volume. For centroids, we're not dealing with weight or mass. Instead, our weighting factors are purely geometric area for 2D shapes and volume for 3D objects. It's a property of the shape itself, not of any physical object.
And looking at the formulas, they look a lot like the ones we've already seen.
That's because, at their core, they're all about finding weighted averages. For a 3D volume, the centroid coordinates are xVOA and so on. For a 2D area, it's xYAA and GAA and ABA. The only difference is what we're using as the weighting factor. Whether it's weight, mass, volume, or area, that's what determines which center we're finding. But the fundamental logic, dividing the total weighted thing by the total thing, that remains the same. It's just like calculating your GPA.
So like we saw with the center of gravity, symmetry is going to be super helpful when we're looking for centroids, right?
Absolutely. If a shape has an axis of symmetry, like figure 7.4.1 shows, the centroid must lie somewhere along that axis. And if it has two axes of symmetry, the centroid will be right at their intersection.
It makes sense. Like a perfect circle, its centroid is right at the center.
Exactly. Question 7.4.2 talks about an I-beam, and its centroid is right at the intersection of its horizontal and vertical center lines. So symmetry often gives a shortcut, since the centroid must lie on those lines of symmetry. If a shape is visually balanced, then its geometric center must lie along that line of balance.
Okay, so now for those of us who aren't dealing with simple shapes, table 7.4.3 centroids of common shapes. This looks like it'll be really useful. It's got the centroid locations for all sorts of basic shapes like rectangles, triangles, circles.
Yeah, it's a super handy reference, but it's important to remember, note 7.4.4, those X and I coordinates in the table, they're always measured from a specific origin point that's indicated for each shape. So if you're working with a shape that's rotated differently, or if your coordinate system is somewhere else, you'll need to adjust those coordinates accordingly.
And you talked about how for a flat plate with uniform thickness and material, the center of gravity is in the same place as the centroid of its area.
Right, because all those extra terms, density, gravity, thickness, they all cancel out in the equations.
So in those specific cases, finding the geometric center is the same as finding the physical balance point.
Exactly.
Okay, now what about more complex shapes? You know, like a shape made up of a combination of those basic shapes. That's where section 7.5 comes in. Centroids using composite parts.
This is where things get really practical. If you've got some complicated shape, we can break it down into simpler components, rectangles, triangles, circles, anything from that table we just talked about.
So it's like we're taking a complex object and understanding it by analyzing its simpler building blocks.
Exactly. It's a strategy that's helpful way beyond just geometry. Break things down into manageable parts, and the problem becomes way easier. And once we've broken it down, we can either look up the area and the centroid location of each of those parts, or calculate them pretty easily.
The key questions in this section are really helpful, I think, for highlighting those crucial things to keep in mind. Like if you've got separate objects, you need to consider their individual centers of gravity.
Right. You find the weighted average of their centers of gravity.
And then there's that tricky question of how to deal with holes in a shape.
Yes. Holes, the bane of many a geometry problem. For a hole, or any cutout area, we treat it as having a negative area when we're doing our calculations. Think of it like subtracting its contribution from the overall centroid.
It's like the hole is anti-area.
Exactly. And one thing that trips people up is remembering to pay close attention to whether the distances to those individual centroids are positive or negative.
Right, relative to your overall axis system.
Yes, that's absolutely critical for getting the right answer.
So the formulas for this composite parts method are XCMEA, XIA, SAA. So basically, you need to know the area of each component, its centroid coordinates, and then you just plug those values in.
Yeah, it's pretty straightforward. There are three main steps.
Mm.
First, you divide your complicated shape into those simpler, non-overlapping parts. And a good strategy is to try to use the fewest parts possible while making sure you cover the entire shape.
And don't forget those holes, those are negative areas.
Exactly. Second, you gather the area and centroid coordinates for each of those parts. Table 7.4.3 will be super helpful here. Just remember to be careful about those origin points. And finally, you apply the composite formulas, summing up all those area times centroid coordinate values for each part and dividing by the total area.
The example in the materials with the L-shaped area really breaks this down step by step. They divide the L into two rectangles and then just carefully apply those formulas. And figure 7.5.2 shows a more complex example with a rectangle, a triangle, and a hole, illustrating how to handle different types of components.
And for those more complicated shapes with lots of parts, it's often helpful to organize all your data in a table, the area of each part, its centroid coordinates, then the products AC and IA. That way, when you go to plug those values into the final formulas, it's much clearer and you're less likely to make a mistake.
So this composite parts method, it's not just for flat 2D shapes, right? It works for 3D objects as well.
Yeah, it's the same basic concept. Section 7.5.2 gives a quick overview of centroids of 3D objects. Instead of area, you use the volume of each component.
So the weighting factor is volume.
Exactly. The formulas become x bar v, xg, and you'd have similar ones for s and z. And if you're dealing with a 3D object that's not uniform in density, then you'd use the mass of each part as the weighting factor to find the center of mass.
Right, because now the distribution of mass matters.
Exactly.
Example 7.5.3 is a great one. It's about finding the center of mass of this composite object made of a concrete block and a steel wedge. And table 7.5.4 lays out how to organize all that data. Volumes, densities, weights, and centroid coordinates for each part.
It's really a powerful method for handling complex shapes.
Okay, so in this first part, we've seen that whether we're talking about center of gravity, center of mass, or centroid, the math behind it all comes down to finding a weighted average. And for these composite shapes, we break them down into those simpler pieces, use their properties and locations, and then we can find the overall center of the whole thing.
It's amazing how we can use this basic idea of a weighted average to understand such a wide range of physical and geometric concepts.
Okay, so for the second part of our deep dive, we're going to move beyond these shapes made of simple parts and look at situations where we've got curves or shapes that aren't uniform. This is where the awesomeness of calculus, specifically integration, comes in.
Yeah, integration allows us to deal with these continuous forms by thinking about infinitesimally small pieces.
Right. Instead of discrete chunks, we're thinking about smooth changes. So section 7.6 starts with this idea of the average value of a function. And I love how they explain it using that visual of the area under a curve. It's like saying, okay, what's the height of a rectangle that would have the same area as the area under this curve, given that they have the same width?
Exactly. The average height of that curve over a specific interval, that's the average value of the function.
Right. So the formula for that average value, I, of a function, fx, over an interval from a to b is I to be fxd, fdA.
Which can be written more simply as fx dx, a dx. It's basically summing up all the values of the function over that interval and then dividing by the length of that interval. A continuous form of a weighted average.
I love how this connects back to the earlier formulas. We're taking the total weighted thing, in this case, the area under the curve, which we can think of as the weighted length, and then we're dividing by the total thing, which is just the length of the interval.
And this idea of summing up an infinite number of infinitely small values, that's how we make that jump from the discrete sums we use for composite areas to the continuous integrals we'll use for more complex shapes.
Right. Our sums become integrals. AI becomes this tiny dA, vi becomes dv, and so on. It's like we're zooming in so far that everything looks smooth.
Exactly. Those centroid formulas we had earlier, like xi, xii, now become XELDA and DA.
Yeah.
Well, it's an ALDA and DA.
So DA is like a little tiny piece of area, and XI are the coordinates of the centroid of that teeny tiny piece.
Like we're dividing the shape up into infinite pieces and finding the weighted average of their positions.
Question 7.6.2 about the average distance between the Earth and the Sun really illustrates why this is so important.
Oh, yeah, good one.
Because the Earth's orbit isn't a perfect circle, the distance is always changing. So if you just take the average of the closest and furthest points, that wouldn't give you the true average distance over the whole orbit.
Right, a snapshot in time doesn't give you the whole picture when things are constantly changing.
Exactly. You have to use integration to account for that continuous variation.
It's all about capturing that continuous change, the entire dynamic process.
Okay, so section 7.7 gets into the nitty-gritty of using integration to find centroids. And the key questions at the start are really helpful, I think. How do we actually set up these integrals? What's this differential quantity dA we keep talking about? And why do we sometimes use a single integral and sometimes a double integral?
Let's break that down. To find a centroid using integration, we use those formulas we just discussed. X-ERI, yes, XEDA. The key is choosing a convenient differential element of area, dA.
And thinking deeper, 7.7.2, what is dA? That explains dA as a tiny, tiny, practically invisible piece of area, like a little speck.
A little bit of area.
Right. And when we integrate, we're adding up all those infinite little specks to get the total area, or in this case, the first moment of area. And that analogy of dA being like the height of a really, really thin strip times its teeny tiny width, dx,
Yes.
that's super helpful to visualize it.
Yeah, it's like we're zooming in so far that those curves look straight, and we're just adding up the contributions of all those little rectangles.
So when do we use a single integral versus a double integral?
It depends how we define our dA. If we're using a thin strip, either vertical, where dA equals y times dx, or horizontal, where dA equals x times di, then we've already kind of taken care of one dimension, and the centroid of that strip can be expressed in terms of just one variable. That's why a single integral often does the trick.
But if we use an even tinier, more fundamental area element, like a little square, dA equals dx di.
Then we've got to sum up those elements in both the x and the y directions. That's when we need a double integral. It's like doing two integrations in a row.
The three-step integration process in section 7.7.1 lays it out really clearly. First, you've got to set up the integrals, choosing your dA and the limits of integration.
And that's where figure 7.7.1 is helpful. It shows those common differential elements you can use.
Right. And then the second step is to solve those integrals, making sure we're careful about the notation and units.
And the final step is to calculate those centroid coordinates using the formulas xQIA and di QXA, where QX and QI are the first moments of area about the x and y axis, respectively.
Now, thinking deeper, 7.7.4 asks, which is better, horizontal or vertical elements? Which is a really practical question because sometimes one way is so much easier than the other.
It all depends on the shape and how it's defined. Like in that example with the curves YOAA equals by 2, using horizontal strips makes the integration way simpler than if we tried to use vertical strips.
Vertical strips would mean you'd have to split the area into two separate integrals.
Exactly. So it's all about picking the way that aligns best with the boundaries of your shape and making sure that your expressions for XL and YL are as easy to work with as possible.
The examples in 7.7.3 really help to see how this works.
They're great for building up that intuition.
Yeah, like with that simple rectangle, example 7.7.6, and the triangle, example 7.7.8, they solve for the centroid using both vertical and horizontal strips, and then even with the double integral.
And what's great is that no matter which method you use, you get the same answer for the centroid.
Which is reassuring.
Right. Makes you feel like you're doing something right.
Absolutely. And then they've got examples with more complicated shapes, the general spandrel, example 7.7.3, the semiparabola, example 7.7.90, the area between two curves, example 7.7.12, and they all use integration.
It's really cool to see the versatility of integration for tackling those non-standard shapes.
Yeah. And then example 7.7.14 shows how sometimes using polar coordinates is the best way to go.
Especially with shapes that have circular symmetry.
Yeah, like finding the centroid of a semicircle.
The symmetry argument quickly tells us the x-coordinate of the centroid has to be 0, And then you can set up a double integral in polar coordinates to find the A coordinate.
And they even talk about how that extends to finding the centroid of a quarter circle.
Super useful.
Okay, so the main takeaway from this part is that if we're working with a shape where we can't just break it into simple geometric pieces, then integration is our go-to tool for finding the centroid.
It's all about adding up the contributions of those infinitely small elements across the entire shape.
And the way we define those tiny elements, our dA and the coordinate system we choose, that can make a huge difference in how easy or difficult it is to solve those integrals.
It's like choosing the right tool for the job.
Exactly. Okay, now for the final part of our deep dive, we're going to shift gears and talk about something called distributed loads.
This is section 7.8.
Yeah, and these are forces that are spread out over some length or area or even volume. It's something we see a lot in engineering and physics problems.
Absolutely. And like those key questions at the beginning of the section point out, we need to understand what these distributed loads are and, more importantly, how we can simplify them.
Because dealing with a force spread out all over the place can be a real pain.
For sure. That's why we need to find a single, equivalent, concentrated force that would have the same effect.
They used that example of a bookshelf, figure 7.8.1.
Classic example.
Instead of thinking about the weight of each individual book, we can simplify it and just think of a single force representing the weight of all the books acting along the length of the shelf.
It makes the analysis way easier. And that's the key here, simplification. To work with these distributed loads when we're trying to figure out if something's in equilibrium, we need to replace that messy distributed load with a nice clean point force, what we call the resultant.
So we need this resultant force to have the same overall effect on the object.
Exactly. And for this to work, we need to make sure two things are true. First, the magnitude of this point force has to be equal to the total area or volume under that distributed load function.
So if the load is spread out over an area, it's like we're finding the area under that curve.
Right. And second, the line of action of this equivalent force, meaning the imaginary line along which it acts, has to pass through the centroid of that entire load distribution.
So for the simplest case, like the bookshelf with all the books spaced evenly, it's a uniform distributed load.
Yeah, so the magnitude of the equivalent force is just the load per unit length, like how much each inch of the shelf is carrying, multiplied by the total length of the shelf. Simple rectangle.
Example 7.8.2 with the paperback books walks through this calculation.
Nice. And where does this force act? Well, because it has to go through the centroid of the rectangular loading, which is right in the middle, the equivalent point force would act right at the center of the bookshelf.
Okay, that makes sense. But what about when the load isn't uniform? What if it changes along the length, like if one end of the shelf has heavier books than the other end?
Then it gets a little trickier, but the same principles apply. Like with a triangular load, where it gradually increases from one end to the other, the magnitude of the equivalent force is equal to the area of that triangle.
1/2 base times height.
You got it. And just like before, that line of action of this force has to pass through the centroid of the load distribution, which for a triangle is located 1/3 of the base away from the larger end.
Example 7.8.3 with the uniformly varying load shows this.
Perfect.
Now, what if we have a really weird distribution of load? It's not a simple rectangle or triangle.
Then we can go back to those methods we discussed earlier. We can either use the method of composite areas, breaking that load distribution down into simpler shapes, or if it's super complex, we can even use integration to find the centroid of that load distribution.
It's all about finding the center of that load intensity curve, which tells us exactly where that single equivalent force should act.
Exactly. It's like finding the balance point of a load itself.
And it's important to remember, when you're drawing a free body diagram to analyze a structure, you only include either the distributed load as it is, or that equivalent point force you just calculated. Don't include both.
Right. That's a common mistake. You'd be counting the effect of the load twice.
Section 7.8.3 touches on how we actually use these equivalent point forces when we're solving those equilibrium equations.
Once you've replaced that distributed load with a single force acting at a specific point, you can use all those standard equilibrium conditions, like the sum of all forces has to be 0, and the sum of all the moments has to be 0.
Right. And that allows us to solve for unknown forces, like those reaction forces at the supports of a beam.
Exactly.
And they've got some great examples to illustrate this. Example 7.8.4, which has a cantilever beam with a uniform distributed load, and example 7.8.5, which has a beam with both point loads and distributed loads. And in both examples, the first step is to convert those distributed loads to equivalent point forces.
It's really remarkable how all these concepts we've talked about, centroids, distributed loads, equilibrium, how they're all interconnected.
Yeah.
They're like essential tools that engineers and physicists use to figure out how structures behave and whether they'll hold up under all those forces.
Yeah. And I love how it all comes back to that simple idea of a weighted average, like figuring out your GPA.
Right. Who knew GPAs would be so fundamental to understanding structural engineering?
Just laughing. That's a wrap for our deep dive into centroids and distributed loads today. Hopefully, this has given you a clearer understanding of how to find the center of various shapes, what those balance points mean in terms of weight and mass, and how to simplify those complicated distributed forces.
These ideas are so foundational in statics, and they'll keep popping up as you explore more advanced topics.
We really appreciate you joining us for this deep dive. It's been fun.
Yeah,
We
definitely.
hope this was helpful and gave you some aha moments along the way.
And if you have any more questions or other topics you'd like us to cover, please let us know. We love getting those listener requests.
Until next time, keep exploring and stay curious.